From false positives to actionable analysis, behavioral intrusion detection, machine learning, and the sock pipe with Joseph Zada. Please make sure that your cell phones are turned off, silent, or on vibrate. We do not need to hear your ringtone. Thank you.
Hello. Well, thanks for coming. The title here is a little long-winded. The white paper that accompanies the talk is called Defense at Scale, Building a Central Nervous System for the SOC. And I think that's kind of the main takeaway I want to leave you guys with today is just basically work we've been doing the last few years, taking the latest in distributed architectures and blending it with cybersecurity analytics. The goal is to kind of go through sort of like my research background, give a brief intro, and then kind of dive into a little bit of like business language, basically a tool I've used to help communicate data science ideas across interdisciplinary teams, and really to sort of try to communicate some of these complex ideas to business stakeholders and people who write the check at the end of the day. And then we'll sort of dive into kind of like the open source community's version of a really cool computing architecture called a Lambda architecture. And just to kind of give you like a sort of a level set, while I was working on these slides, the company that we were originally doing all this work for, Caspita, was acquired by Splunk. So I've sort of reappropriated all this content and just try to make everything consistent. So let me see here. So just to start, I just want to kind of give you guys a level set on how I got here and why I think artificial intelligence and cybersecurity is such an interesting problem. From a security perspective, I was playing around with like John the Ripper, Loftcrack, 15 years ago. First DEF CON I ever attended was DEF CON 8, and I went to a talk by a guy named John Erickson. He wrote Hacking the Art of Exploitation. He gave a really crazy talk called Number Theory, Complexity Theory, Cryptography, and Quantum Computing. And it was just this, like it was sort of, I was very impressionable at that age. And it sort of planted the seed. As a young researcher, I've been sort of trying to understand like the security community and sort of the depths of the interdisciplinary nature of some of the really cool research that you guys do. And so I think it's basically just kind of studying cool security problems has sort of led me down this weird research path. While I was kind of interested in security as a hobby, I was working in a network operations center. I was building tools like MRTG, first generation NMS systems, like I was using like HP OpenView, Cisco Works, and we were doing like a lot of layer 2 profiling of switched and routed traffic and kind of protocol baselining, stuff like that. And so kind of when I was first exposed to machine learning was really, was more for kind of benign physics, the dynamics of certain processes that occur in physics. And so here in this slide, there's a few kind of time series of sort of chaotic effects that we're studying at really large scales. And we're using just some different techniques. One of the sort of standard tools in machine learning tool set, for instance, we were using a lot of Markov chain Monte Carlo to make predictions on sort of different physical models. One of the models that was sort of most interesting to me that kind of like led me down a rabbit hole towards kind of defense and artificial intelligence was a model called Stochastic Fast Dynamo. Stochastic Fast Dynamo is sort of described in kind of the middle picture here as if we understand this toy model for the dynamo. The dynamo is a fluid that moves in the Earth's core. It's sort of molten iron, and the dynamo is basically the effect that's generated by this superfluid moving and generating a magnetic field. So if we're able to kind of predict the properties of this evolution of this fluid, we can make predictions on when the Earth's pole is going to shift. And this actually has pretty deep implications for like climate change and long-term macroscopic effects that impact our whole Earth. And so it kind of became a really interesting question, like how far can machine learning get us in terms of predicting like black swan major outlier events, like when the next asteroid's going to hit. And so that was just sort of an interesting question that I started learning more about, and then I started studying climate change too. And my advisor at the time showed me this graph because he was basically modeling. We were using machine learning to help us make predictions about future climate evolution. And he kind of pointed out this graph, which is, I mean, it's a pretty morbid in some sense, but this is the graph of extinction intensity for species over time for the last like 500 million years on planet Earth. And the 5 annotated events are sort of the 5 labeled extinction events, where the peak here we've seen like I think there's one like large period of heightened volcanic activity a long time ago where 95% of all unique species on planet Earth were wiped out. And I don't know, it's sort of a weird connection to make to these sort of longer term effects, but I was studying these phenomena and using the tools of a lot of time series prediction tools and other kind of machine learning methods to help us make predictions on really big questions. And eventually I sort of was led to seeing how researchers in cybersecurity were grabbing some of these tools and applying them to really interesting use cases. So now to kind of dive into the cybersecurity side of things, just want to start with a motivation on why defense is so hard, why working in a SOC is really challenging, and how we can augment defensive workflows in the light of some of the asymmetries in offense and defense. And probably my favorite asymmetry to highlight, these are sort of just key takeaways from 2 keynotes at Black Hat. One was Mudge's, one was Bruce Shiner's, and I think I sort of like grabbed all this data actually from practical malware analysis. But basically, this is just sort of a breakdown in an analysis that DARPA did on the number of lines of code for just offensive weaponized code versus defensive products like firewalls. And it's sort of a proxy in a way. If you hear Mudge, like what he's really trying to explain in my mind is that there's an asymmetry between the unit cost for being on defense versus the unit cost for being on offense. Meaning, offenders put a lot less resources into. We'll see PHP scripts that are weaponized that are like a couple hundred lines of code. And in the other extreme end of things, you'll see like a checkpoint firewall, which is 10 million lines of code. So this asymmetry really highlights a property of defensive techniques that I want to sort of emphasize as a philosophy. So this is sort of the way the teams I've been working with have really approached kind of reconciling this asymmetry between offense and defense, and it starts with a real simple generic quote. I stole this from the Joe Rogan podcast. This is from a undefeated samurai. He lived a long time ago, and he wrote a book called Book of Five Rings. And the quote is, "Once you understand the way broadly, you can see it in all things." And I think I try to take a little nugget of this and apply it to the work I do. And I mean, this is sort of a loose connection, but kind of what he would talk about is once you see how to master a sword, you see that same kind of art in a tea ceremony or in like the bonsai trees, and it was just kind of an interesting dude. He would fight to the death, and he never lost a battle. So the way I take away from this book is basically he sees the world as this kind of fractal, this fractal philosophy. I'll describe what I mean by that. And part of the time series I was studying, the reason I sort of use this word is this was really baked into the language of the research I was doing. So we were studying these time series that over like long periods of time, they have this fractal property, meaning that if you zoom in on a particular section of the time series, there's certain information that scales across the different levels of zoom you have. Kind of a better way to put it, for example, is like a fractal is an object in nature that exhibits a sort of repeating pattern on many scales. Like a great sort of cliche example you guys probably might have heard is if you look at the number of leaves in a forest, the number of leaves in a tree gives you a sense of the distribution or the population size of the trees in a forest. So it's that sort of similar information on many scales. Also, like your cell phones, for instance, the fact that the antenna inside our cell phone is leveraging a fractal geometry to optimize the just energy ratios. So in our context, and I'll explain what I mean by this sort of in a concrete mathematical formula in a second, is that we try to take this approach to scaling defensive tactics at a very is core part of the philosophy, really with respect to kind of how Mudge was highlighting this asymmetry between offense and defense. And so kind of how this is manifested for us, like when we do this modeling in kind of commercial applications or just one-off custom analytics, we end up having sort of reusable use cases and reusable code. And really this kind of comes down to like appropriately modeling and decoupling like the complexities of certain traditional rule-based systems. So we use this sort of idea of like the behavioral IOC, like a behavior-based indicator of compromise, to really sort of generalize what it means to have an alert from snort, or a behavior-based, like a sort of a sequence of weird exploit chains that are kind of just that particular pattern has never occurred in your entire corporate data. And so we leverage these kind of ideas like the behavioral indicator of compromise to map more to techniques, tactics, techniques, and procedures, the TTPs of the threat actors, versus the actual lower level kind of indicators that are easy for the threat actors to change with just one line of code or a simple sort of tweak. And I'm not going to try to get too mathy with you guys, just to give you a sense of what I mean by sort of the fractal nature of abusing this idea. So we have two use cases that we kind of apply this like just kind of think of Formula 1.1 as it existing as a piece of code, and it's just sort of a special permutation of what we mean by behavioral indicator of compromise. In this case, we're just using it to come up with an n-gram score to detect pseudorandom domain names. This is pretty much like the most talked about example in machine learning for cybersecurity. So I don't want to elaborate on this too much, but basically we use this formula for the use case of pseudorandom domain name detection. And then we use a very similar formula. It's based on the same notion of leveraging our data, but it's implemented a little bit differently. And this model is applied to exploit chain detection. So it's a completely different use case, completely different behavior, and this kind of lets the defender be more sort of fractal in exposing kind of cool, just interesting signals in a way that they're easy to blend together in the right layer of computation. So when this is all said and done, what we end up with is this central nervous system approach that, I mean, it's sort of a kind of a naive analogy, but like the point solutions are really good at certain things that they're designed to do. Like if FireEye gives me an alert, and then I get an alert from a snort, and I also have something interesting about those two alerts that I can say statistically, like the FireEye box caught a download that was, there's associated some external IP address, and we've also seen that IP address with periodic traffic. There's only one user in the entire network of 10,000 users that's talked to the IP. There's all this sort of little weak signals of data-driven evidence that we can combine with sort of the static signal from the point solutions, and basically blend together an overall score for the behaviors. So we'll kind of dive back into this picture a little bit later on, but from a machine learning perspective, what we end up doing with this G, like how we score a cluster, how we sort of blend all these signals together, is typically this is either learned through some supervised learning algorithm, or a lot of times it's almost hard to beat what a security analyst will engineer heuristically for this G. So anyway, so that's just kind of, this is sort of a loose introduction. The key takeaways we really want to leave you with are three main sound bites. I hope they're practical and not too hopefully there's not a lot of math or sort of complicated ideas behind it, but the first one that we tried to articulate here was the fractal defense. And it's just sort of a way to kind of brand some of this stuff. So the cybersecurity analytics paradigm is something I've been working on for a while now, and I've noticed I've noticed a couple of issues. Like one, a lot of the engineers we work with who don't necessarily bring security domain expertise to the table have a hard time decoupling like the sort of the infinite possible behaviors that manifest in kind of the different stories we see in the news. And so I kind of call this kind of making the mistake of looking at the threat surface as sort of a continuum of different behaviors, more from a machine learning perspective, because a lot of literature out there will end up without mapping a particular machine learning algorithm to sort of a security primitive. And I'll show you guys what I mean by that. So the goal here is just sort of like, one is to just motivate a way to describe what it means to rank order different cybersecurity analytics. And I would use this kind of language a lot to just help just bridge the communication gap between like data scientists, security researchers, and business stakeholders. I mean, a lot of times when you're working on these problems that in enterprises where the number of users is so large that the SOCs just don't have enough time to even really think about this, we're kind of always playing this this game of catch up. And so this is just a way to sort of insert the cybersecurity analytics into the conversation and help roadmap in the bigger scheme of all the day-to-day SOC activities. So and just kind of want to walk you through sort of how I do this, basically as just from a philosophy perspective. I mean, this is, so pretend we're with Acme Corp. I mean, this is, as a consultant, I would do this a lot. We would get like a list of, kind of jump ahead here and just show you sort of like, pretend we're just, dealing with a conversation on how we want to kind of better mitigate particular attacks that we don't have coverage for yet. So we're sort of enumerating our threat surface and just sort of listing the use cases that are top of mind for security, for the business stakeholders. So this is, I'd play this game a lot. I would get in a room and we'd say, okay, these are the 5 use cases that are most top of mind for us. I mean, and they run the gamut. I mean, there's so many things. In a large environment, we see, I mean, and I just kind of sort of scattered some of the most common, a lot of the common things I've worked on or are just popular recently. So kind of think of getting this big grab bag of use cases that sort of is trying to enumerate the threat surface. And we kind of just take your favorite list of use cases, and the next step is to determine coverage and impact risk, which is sort of a fun exercise for business stakeholders. And I don't think it's really practical for most shops. Really large shops, like I know Microsoft has like a bunch of data on the cost of breaches, and so if you're able to calculate this stuff, it's pretty actionable for the business side of things. But I think for a security intuition, security researchers and analysts know, like detecting command and control in general is maybe just like has less of an impact than detecting someone that's walking the entire OU tree with a sort of past the ticket footprint a little bit ahead before that. And then the third step is to sort of express this stuff in a couple simple dimensions so that we can then come up with a ranking for the different use cases in the threat surface. So this is kind of just taking all these use cases. I mean, we can think of millions of different possibilities, but at the end of the day, in my mind, it just comes down to coming up with like a basic formula or a basic approximation. So what it means to have one of the return on investment for investing in one of these use cases. And I kind of wrote a simple formula down here. I would show, like, I use this at a couple companies. I don't think this is right, but I wanted to put it down as a way to kind of motivate the conversation and more debate on what is important for really measuring the value of a cybersecurity analytic. And for example, like the way this started happening is what we would do is we'd stand up a couple of analytics in the sort of the WAN side of detection. So we'd have like command and control detection and maybe exploit chain detection. And then we would sort of operationalize those analytics and have the SOC team just as part of escalations every day triage the output. So you think of like one row of output occurring for like one of these custom solutions. we would measure the time it took for basically the validation of the security researcher to say, oh, this is true positive or false positive. So in the WAN, we see like when we give them external IP data, who is information, on average it would take a security researcher an hour to validate one of these WAN analytics. But in the LAN, like if we had like an AD, Active Directory based machine learning driven analytic, on average we were taking the shop I did this, it was about 20 hours per row of output for kind of the pass the hash, pass the ticket detection in the LAN. And this kind of let me just sort of crudely approximate what I meant by value. So in terms of value, whoops, sorry. What to me the most important thing from a practical takeaway working with the SOC was not only the impact risk, but just the cost of validating the tool, the technology, the analytic itself. And so the value of the solution is actually kind of on the y-axis, and on the x-axis is sort of the cost of the validation. And in sort of my experience, there's I mean, this is such a crude approximation to a very complex problem with many dimensions. So one way to sort of augment the graph without adding another axis is just to kind of bake in the information from the signals for sort of the different components of your infrastructure. And in particular, why I think validation cost is so high and why I think this is a big issue in general on defense is because of the lack of visibility into the LAN. And so one of the organizations I was doing this on is, I think the number of users is around 250,000 users, and they have such large data centers that these data centers have like thousands of users traffic, but because it's architected in such a way that it's like a giant black hole, like it's like all switch traffic. So you lose a lot of signal for sort of the lateral side of things in the LAN when you're doing modeling, and particularly machine learning modeling. I try to target a sweet spot. So we kind of approach where we think the machine learning is going to give the best output in terms of augmenting human workflows. And that means like just minimizing the cost of validating. So sort of after all is said and done, and just different organizations will have sort of different permutations of this graph, but there's always a sweet spot, and there's always a way to basically prioritize a ranking, saying, oh well, I'm going to start if I have a year to assign a team to adding some new coverage for maybe a set of use cases that are top of mind, I'll prioritize them based on sort of this little ROI graph. So this is just sort of it's more of a communication tool. It's very kind of loosely defined, and there's a lot of dimensions here that I totally omitted. So and this slide is actually thanks to Manzi Mirza at Splunk. I commandeer his graphics. I think this might be on a blog already, but he kind of put this together as a way to show. He uses this to kind of explain to customers when we're talking about modeling the threat surface, we really have to take into account adversary capability. And I think working with machine learning researchers who kind of have to read about the gamut of extreme attacks that are sort of nation state driven all the way down to much less benign and less adversary skill, it becomes a challenge to decouple the adversary model from the rest of the algorithm in some sense. So my position is always to sort of start from low to high, especially if you're a machine learning researcher, and try not to model the nation state. This is really where you need the most advanced technology in combination with like sort of the best human workflows. Like start from low to high. And so the other kind of thing we run into a lot when just over the last year, I probably built like 20, not me personally, but just the team we were working on, we'd seen, 20 to 25 machine learning algorithms, specific models we had to implement, we had to benchmark. The majority of these models in cybersecurity don't even have any data. So you're sort of stuck in a weird position where like, okay, maybe I can simulate data at a small scale and try to generalize, or maybe I can try to collect open source intelligence and build some statistics off Contagio. But the cool thing we've been finding over the last year, especially kind of thanks to DARPA and a website called predict.org, is they're really spearheading, in my mind, what is sort of the next step in the evolution of defense, and particularly like leveraging some of these techniques from the machine learning community that really rely on good annotations for samples. And so there's just a few data sets here that I think just want to give a big kudos to. These are really awesome data sets. So if you're working on any of these kind of problems in general, like where you really have to model the human, like isolate a human behavior and see sort of the diverse footprint they have across email logs, across LDAP data, across firewall and WAN, it is such a complex mix of heterogeneous technologies that it's almost not worth simulating. It's better just to get something existing and something that's really been handled appropriately with a lot of resources. Kind of the other, this also kind of touches on just a topic I think is really important to emphasize, like as someone who's a stakeholder or someone who's on the defensive side of things, like you'll be more and more in the space of dealing with these next-gen solutions, and how do you benchmark them? And part of what I've seen working with SOCs and dealing with like the constant fire drill of just evidence collection and day-to-day escalations, it's hard to leverage the information from the SOCs workflows in the machine learning path without some sort of normalization. Like typically, like I'll work with one researcher who keeps all their evidence notes in Sublime, and then another researcher will keep all their notes in Excel, and there's not like sort of a normalized format like that describes sort of the output of sort of the evidence collection that's annotated specifically for machine learning. So that's just hopefully something you can gel on, and then and just to sort of emphasize that further, this is what Bruce Scheiner said in his Black Hat keynote last year, was the real problem in security is requirements are non-functional. So that, in my mind, from a machine learning perspective, the first step to making something functional is to define, like to describe a well-defined behavior you want to model. And then once we know what that behavior is, like exploit chain detection, I can go to the malware dump and just pull down all the whole set of exploit chains for last year and validate that with a set of known examples. So that's sort of what I mean by just kind of emphasizing the functional requirements. Okay, so hopefully that wasn't like too boring of a kind of business side of things, but just the big takeaway for me from that part of the content is just it's been a very effective tool for communicating across teams. So hopefully that's what you guys use it for. And then kind of finally here we get to sort of the meat of the technology, sort of what platform we've been doing all the machine learning on. Well, it becomes a problem of doing this at scale. And what we want to do is help augment or just provide a way to make this loop between a security analyst and the SOC. We just want to augment this workflow as best as possible. So one way I kind of like to think about this in a super generic, like an algorithm terms, is when I work with security researchers, like they have this very sort of expressive kind of search path they go down. Like you kind of give them different evidence, depending on the use case, and there's sort of this very giant kind of tree of information that they build based on evidence and pivoting off certain things, like, oh, this subnet had something interesting that we saw a gate.php, and kind of just going back and forth off little indicators. You'll eventually kind of see this like decision tree process that takes place. And so that's kind of like the goal here, to capture part of this decision tree, this human domain expertise in code and in a platform. And so that's kind of what I'm excited to talk about, particularly in the context of security, because I haven't seen this language mentioned a lot, and the first time I saw it originally, I think, was one of Nathan Marsh's talks on Storm in 2011. Storm is an open source architecture for doing real-time computing at scale. It's kind of like I guess it's the biggest followed Java project on Git, but it's a really cool platform for doing distributed computing real-time problems. And Nathan was dealing with this problem of calculating different analytics for Twitter at scale on really large amounts of data. So kind of where I kind of first heard this, so the term was originally coined by Nathan Mars to describe a generic problem-solving approach that scales to extremely large data processing tasks. So he was, and this is the quote from his talk. So at Twitter, we have our batch layer constantly override the real-time layer so that if anything ever goes wrong, it's automatically collected within a couple hours. That batch real-time approach is really general. It works for pretty much any problem. It's something I really recommend, and it's a deep topic. And what Twitter and a lot of kind of classic non-security use cases are using this for is more to kind of blend the best of both computational paradigms, which is batch and real time, and to use it in a way to have the most accurate picture of the analytics you can. In security, we can kind of like leverage this architecture in a little bit different of a way. So the breakdown of the Lambda architecture, kind of the way Nathan Mars describes it, is just a set of functions. So 3 functions that describe 3 different views of like how to process data in different paths. And if you check out his talks, I have a whole list of sources at the end. I'll kind of show you sort of where exactly you can see these. But they're really interesting talks, and he's sort of he's one of his talks is called like a call for sanity in the NoSQL community, and it's about the fact that and this is what I've seen working on SEMS, first generation SEMS for the last 20 years. They've done good up to a point, but there's a bottleneck in the computing, and the bottleneck in the SEM is basically the data processing path. That's really a computing paradigm is 20 years old. So they mix the transactional nature of databases and sort of historical updating and all the stuff that happens in databases. So they mix all this in kind of one computation path. And what we're learning from like shops like Google and people who are doing this at really large scales is if we sort of decouple the computation in sort of a very special way, you minimize all the complexities of update and write into your real-time path. And this makes these systems much more fault tolerant, much more resilient, and more importantly, they scale to the size of the data sets that are important to make actionable sort of analytics for security. So this is, we elaborate a little bit more on this in the white paper, but basically the point here is that a Lambda architecture, and this is sort of what I've been building in one form or another, just using different systems. At first it was proprietary parallel databases. Now we've used Spark, Hadoop, Storm, the Apache ecosystem. And what it is, it's a way to kind of put a bunch of components together in a processing path that is extremely resilient and can take the size of a corporate perimeter traffic set that's updated every day. Some of the cool things I've seen these architectures doing, for instance, like one of the last projects we were at, where they not only did they kind of use it as an ingestion path, but because there's sort of a resource manager and basically something at the back end of all this, like a brain that is kicking off threads in a computing cluster that's in a distributed parallel, basically parallel computation path, where certain threads would actually be turned into crawlers or worker processes that were touching large parts of our internal data stores, grabbing all just open file shares and looking for compliance violations for PII detection. So we use these crawlers to sort of augment some of the common forensic tasks. Similarly for like watering hole detection on kind of crawling content on web pages. So there's a lot of ways you can kind of, once you have this architecture stood up, there's a ton of parallelism and just powerful things you can do with it. And I think kind of that one of the key things we see in in really standing this kind of technology up in a shop where they actually want to make use of the analytics. It's not just some standalone piece of code that a data scientist worked on and it gets shelved, but actually operationalizing all this stuff and feeding directly into security operations center feeds. A really complex question that we didn't really touch in the white paper is how to stabilize our models and how to age a new analytic versus an old analytic, and particularly taking into account Mudge's notes on the asymmetry of offense and defense. We're going to be dealing with concept drift, meaning our labels are going to change over time. So this particular part of the operationalization is really important for ensuring that we are making the best analytic choice possible in an automated fashion. And I have to thank Marius for this slide. This is actually one of the engineers who's just super cool to work with. He kind of architected all this stuff, so this is a commandeered this slide. And I think for me, just thinking about this Lambda architecture, I mean, it's such a deep topic to just try to gloss over really fast, but it's more of, again, it's more of a philosophy thing. And I think one way to think about it, I'll kind of show you guys how it sort of visualizes in actual computation in a second, but I think, for instance, a great example of what you want to do in a batch path, which is super simple. I pretty much do it in every analytic that's looking at outbound stuff, is we use a statistical whitelist step. So in our batch step, we take each IP address, each external IP address, and each external domain name, and we just do a popularity check. We say, what is the number of unique users that's talked to this, or the number of unique internal IPs that's talked to this domain or this IP address? This is just a super simple calculation you can have periodically updated once a day in your batch layer. And that little statistic kind of lets you analyze the different levels of strangeness that in outbound traffic. Like you can say, okay, let me just study all new domains that have less than 5 users that this is the first day we've ever seen data. And right there, you can already start to kind of zoom in on certain types of badness. So I think this should be baked into security products in general. I don't think there should be any reason why we're just leveraging streaming inline solutions for everything. Like the perimeter can leverage historical data, and I would love to see it in firewalls. So kind of one sort of theoretical kind of like caveat to mention here is, I mean, this is at a high level where we're kind of glossing over some of the depth to doing this type of computation in a highly scalable distributed system. There are certain computations that don't scale across parallel processes. This is kind of from a CS perspective. This is the class is P-complete and NC. And think of if your algorithm is of class NC, it means it's sort of embarrassingly parallel. And certain problems where you have to sort of merge state all into sort of one thread of memory or one place, like a median, for example, just they don't inherently parallelize across a cluster. So I think we just have a couple more minutes, just kind of give you like a sense of sort of how this stuff manifests. I mean, we couldn't really do any demos or anything. We do have demos at the Splunk booth, but just when you build a Lambda architecture and you stand this type of thing up, what you're able to do is come up with expressive ways to model TTPs, and not just a simple rule, but more like a structure where there's encoding in our edges, where there's a particular behavior we want to model. So for example, if I want my analytic to study the properties of mobile command and control, when a threat actor is sort of evasively moving the C2 every so often, well, I can kind of express this in this general framework of sort of the behavioral indicators of compromise on the Lambda architecture. Similarly, like another sort of example, just kind of walk through really quickly here, is just we call like the perimeter pivot, where basically a DMZ facing asset is compromised, and then it's used to establish a beachhead, which eventually we'll see someone talk to a domain controller eventually, or something along those lines. So sort of how this is all kind of visualized is we can hunt for these type of TTPs in a processing framework that first takes a bunch of data, doesn't look like anything, does a simple sort of in an automated way, is constantly in real time updating new sessions, tracking users, mapping them to IP addresses over time, and finally, at the real time step, doing a check to see, is there something funny going on with a particular part of our social graph? And that's exactly what I was sort of showing originally in the intro, is kind of hunting for a way to express what it means to find one of these clusters, a high-risk communication cluster. And it's sort of exactly this thing at the end of the day. It's about putting like the best part of the rule systems, like the FireEye boxes and the snort boxes, in combination with behavioral-driven techniques. So each one of these Fs here is either a classical point solution alert, or it's a behavioral-based, it could be a whole machine learning algorithm, or just like a simple feature. So this is sort of the idea of scaling up and down the defensive ladder. So, and I think we're out of time. I don't know if, just a couple, 10 minutes? Okay. Maybe, I mean, just sort of talk more about like the theoretical side of things a little bit for the like the artificial intelligence kind of angle. I mean, I think it's just such a cool question to think about what it means for can a machine think? And a lot of theoretical people have put a ton of work into saying what it really means to like how far we can go with a supervised learning algorithm in machine learning, and particularly. If you come from this community, you probably are aware of these things called the no free lunch theorems. I think it's important to be aware, just take Mudge's example of the lines of code and realize that pretty much implies we're always going to have adversarial drift. So adversarial drift really means that the labels change over time, in which case we're sort of in the problem space of no free lunch. So that's just sort of one kind of theoretical thing to take away. The other kind of thing I like to think about is like sort of what are the limitations of in artificial intelligence in general when I know some of these crazy counterexamples. Like I think a sort of random paper to cite is Travis Goodspeed, Packets and Packets. It basically shows that given a communication medium, we can always embed a covert channel into that communication medium to avoid eavesdropping. And so in some sense, we can sort of phrase that as, will a communication contain steganography? And is that even a tractable problem for machine learning? And well, I think this isn't really the right way to phrase it. It's not equivalent to the halting problem, but I think the halting problem is sort of a good. I feel like we're constantly running up against the halting problem in cybersecurity. I originally saw someone from Veracode had this on their Twitter handle, how she always, basically her day job is looking at poorly written web apps, and she's like, pretty much I'm cheating at the halting problem. I'm trying to guess if a program's going to crash or is exploitable. I like that philosophy. I think there is something to be said about what is the limit of an algorithm in terms of detecting steganography or any of these things, an exploit. How far can we really go? And for sure we know the halting problem, the reason I sort of put it up here is the halting problem is famous because it was one of the first problems proven algorithmically undecidable. It's kind of, it's crazy. I mean, Turing proved this in 1936. What's sort of interesting from like just a sci-fi artificial intelligence perspective is it is actually an open question whether any such unknown physical processes are involved in the working of the human brain and whether humans can solve the halting problem. So maybe that's why security analysts are so much better than computers is I think we're sort of running up into these places where it's sort of known theoretically that algorithms aren't usually just the sole solution for these problems, and that's why a human algorithm augmentation is, in my perspective, is we want to build these things to really augment the humans as best as possible and sort of close those loops in the SOC. So yeah, that's I think we're kind of good on time now. So maybe I'll just open it up for, just so the sound bites here, just hopefully the key takeaways are, I mean, I hope this was useful. Fractal defense, cybersecurity analytics, ROI, and Lambda architecture. I mean, gosh, and there's so many sources, like the white paper is a lot better source. It's a little bit more technical. It's kind of written academically. There's so many sources to cite here. I know I overlooked certain people to cite in the slides, but the list of literature is just huge, like that I think is important in this problem space. And yeah, so let's just maybe open up for questions. And I think there's like a mic. If people want to ask questions, they have to come to the front. And I guess there's surveys. If anyone, if you guys just leave your survey on your desk or a chair, I mean. Thanks.